Hi, good morning. Today we are going to continue to review the related rate problem. Let's take a look at question number 1. Oil is leaking from a pipeline on the surface of a lake and forms oil slick whose volume increases at a constant rate of 2,000 cubic centimeter per minute. The oil slick takes the form of the right circular cylinder, with both its radius and height changing with time. The volume V of the right circular cylinder with radius r and height is given by V equal to pi r squared h. At the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeters, the radius is increasing at the rate of 2.5 centimeter per minute. At this instant, what is the rate of change of the height of the oil slick with respect to time in centimeter per minute? So now we are going to analyze this question over here. So we have a circular cylinder. So it says that the R and the H are function of time. And definitely the V is function of time. The volume increases at the constant rate of 2,000 cubic centimeter per minute. It tells us basically dV dt equal to 2,000 because three-dimensional, and the volume is positive because increasing. Now we continue to read. When the radius of the oil slick is 100 centimeter and the height is 0.5 centimeter, so the R equal to 100 cm and H equal to 0.5 cm. At the moment, and the radius increasing at the rate of 2.5 centimeter per minute, so dr dt equal to 2.5 cm per minute. So at this instant, what's the rate of change of the height of the oil slick with respect to time? So basically, we asked to find dH dt. So now we have all this information related to R and H in the V, and this is the equation that relate all this information together. So we are going to find the derivative of this function with respect to time. So we have to find dV dt, dr dt, dH dt using this equation. So V equal to phi pi r squared h. R is a function of time, H is a function of time. So therefore, we're going to use the product rule. I'm going to make U equal to pi times r squared and V equal to h. So now we're going to have U prime equal to pi times 2r times dr dt and V prime equal to dH dt. So dV dt equal to the product rule. So we get pi times 2r times dr dt and then times h and plus pi r squared times dH dt. So now we are going to substitute information. So we get 2,000 and pi stay the same, 2 and times the radius, and the dr dt is 2.5, h is 0.5. So after we did the substitution, next step we just do the regular algebra to solve for dH dt. So we have this multiply, you can use a calculator, and this will be, now we're going to subtract 250 pi both sides, and then we got 2,000 minus 250 pi equal to this. Next, divided by 10,000 pi. So cancel. So you get dH dt equal to this fraction. You can leave the answer as a fraction, and then this one dimensional, so therefore cm per minute. If you want to convert this fraction into decimal, so you have to type in this way. You have to enclose the numerator in parentheses and the denominator in parentheses. and then let's type it in the calculator. Okay, so this will be the final answer in decimal if you convert it into decimal. Of course, you don't need to convert your answer in decimal when you take the AP exam, just in case you need to. So don't forget to put the numerator in parentheses and denominator in parentheses if you have a pi especially. Now let's go to part B. So part B, it says that a recovery device arrives on the scene and begins removing oil. The rate at which oil is removed is RT equal to 400 square T cubic centimeter per minute, where T is the time in minutes since the device began working, and then oil continue to leak at the rate of 2000 cubic centimeter per minute. Find the time T when the oil slick reach its maximum volume. So the keyword is find the absolute max of oil in the oil slick. So we're gonna let P of X equal to P of T equal to the amount of oil in oil slick. You don't need to use the P of T or P of X. You can stick with the letter V if you want to. So now let's analyze this problem a little bit. So this is the oil slick. So oil continue to leak at the rate of 2000 cubic centimeter per minute. So that means the 2000 cubic centimeter per minute is the rate in to the oil slick. So we get rate in equal to 2000. And then the device, okay, remove the oil at the RT. That means the oil was being sucked by the device at the RT equal to 400 square T. So this is the rate out. The oil got removed. So we get rate out equal to RT. So now this question turned into a problem that we had know before. I called the water in and out problem. So let's refresh our memory. So we say that if you let the P of X or P of T equal to the amount of oil in the oil slick, so P of X equal to integral. So the starting time, okay, I'm gonna call it A. So we're going to find out is beginning with 0 and not later on. Okay, so A to X, T, okay, X. So this to match. So we get rate in dt minus A to X, and then rate out, and then dt, and plus the initial amount. Okay, so now we are going to find P prime of T. So we say that the P prime T equal to the rate in minus the rate out. The reason is you take the detailed integral. Okay, so basically it becomes the rate in and rate out. So P prime T equal to 2000 minus RT. We're going to make the first dt equal 0 to find the lattice max. So therefore we get 2000 minus 400 square root T equal to 0. And then we solve for T. So we plus 400 square root T both sides. So we get 2000 equal to 400 square root T. Divided by 400, we get 5 equals square root T. And then T equal to 25 after you square both sides. So now we had to check, see it at 25. That's really going to be the absolute max. So we get P prime T equal to 2000 minus 400 square root t. So you can use t equal to 1. You substitute 1 over here. 2000 minus 400 is positive. You can use 100. So 400 times square 100, it becomes 400 times 10. So therefore 4,000. 2,000 minus 4,000 is negative. So now at P of 25 is the only Larited max. So there is one Larited max, which is P of 25. So P of 25 is the absolute max. So now we are going to paraphrase a little bit. So therefore I said that at t equal to 25, the Hoyle's leak, which is maximum value. Okay, so therefore we finish part B. Now let's go to part C. Part C is that by the time the recovery device began removing oil, 60,000 cubic centimeter of oil has already leaked. So write but do not evaluate an expression involving an integral that gives the volume of oil at the time that found in part B. So basically, in part B we found out the time is 25. So now we go and say P of 25. You define the amount of oil at t equal 25. So when the recovery device begins, so we call that moment is t equal to 0, and then 25 is the maximum. So 0 to 25, 25, 25. So the rate in is going to be 2000 dt and minus. So 0 at the moment the recovery device arrive. At that moment it begin to work, we call t equal to 0. Okay, so now we got integral rate in minus integral rate out, and then plus the initial amount, that is the time when the recovery device arrive at the scene, so which is 60,000. So now we finish writing the answer for part C. Is that write but do not evaluate. So we just write down the integral expression for P of 25, and we do not calculate. Now we finished question number 1.